This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
Paul Verschure here with the Convergent Science Network podcast. I'm here with Viktor Jirsa. Viktor, welcome. You were speaking today at VCPT 2018 about translational neuroscience with a very strong emphasis on that's a whole brain perspective on epilepsy, right? So there are two issues here. Why epilepsy? Why do you think epilepsy is a helpful lever to understand how brains work or not work?
Enough. So first of all, hello. Nice to be here. I have chosen epilepsy for a variety of reasons. But epilepsy is a dynamic disorder. It expresses itself through very characteristic features, spatially and temporally. Temporally, you have high frequency oscillations that are, if you happen to have the electrodes in the brain, that are visible with the eye, essentially. So you have very clear data features that you can recognize that are then also linked to the semiology, to the signs, to the clinical signs when the seizure onsets. That makes it unique. Yeah, it's also spatial because it involves a network. We talk about epilepsy spread. The seizure spreads through the network. From a perspective of someone who wants to model the brain, someone who wants to understand emergent brain function or dysfunction, here you don't have to look for the features. They're evident. They have been documented for a long time. They are linked to characteristic behavioral patterns. Yeah? When you look at other diseases or disorders linked to the brain, it's much more difficult. What you do with schizophrenia, what you do with bipolarity, what you do even with multiple sclerosis, where you have a structural equivalent, when you want to measure the function or the impaired function, what you look at in the data, in the measurements, it's extremely difficult. So even already at the first starting point, you run into difficulties. And epilepsy promised for me a wonderful entry point, enabling me to apply some of the tools that were under my control. Yeah.
So how long ago did you start with epilepsy?
Epilepsy, we started 7 years ago. I followed epilepsy before a little bit, but more as an interested observer, fascinated by the dynamic features. But epilepsy per se, the first time I touched epileptic data was 7 years ago.
So epilepsy was among the Greeks known as the holy disease or the sacred disease, right? Because it was believed that it had supernatural features. So what are the key features in epilepsy that you think you should try to understand and control?
There is a number of features that come to the mind. Epilepsy is fairly widespread in in its expressions. It depends on the type of epilepsy that you look at. Today in today's talk, I showed you a patient with a prefrontal organization of the network involving the temporal lobe, and the behavioral features are fairly expressive in the sense of behavior. These were normal behavioral features. You would not know. If you isolate some of these features, you would not think that this is an epileptic seizure, such as rocking of the body or crossing the legs. Yeah? So in other features, you just have these muscle spasms in other seizures. Yeah, one of the key features we need to get under control is when the seizure propagates and spread out through the network, it starts taking away control for the patient. This is one of the most horrible experiences for the patient, that the patient starts losing control of her behavior. And that is often not linked to the onset of the seizure, but actually to the propagation of the seizure. So when you talk about some of the features we would have to get under control is to improve the quality of life for the patient. If we can limit this type of impairing features on the behavioral level and just constrain the epilepsy, the discharge from propagating, from spreading through the network and recruiting other features, other areas, this would be a wonderful feature to get under control. Another feature that often is being evoked is loss of consciousness, which is also often linked to the propagation of the seizure. This is horrible for a patient when she knows that she can lose consciousness at any moment now. When the aura appears, then the patient already knows I may be able to lose consciousness and driving a car. This is very debilitating and constraining feature for the patient.
Right.
Yeah.
So now you pointed already to an important step then in your approach, right? Because then the surprising thing, I guess for the classics, the symptoms could be so variable. It might indeed be loss of consciousness. It might be vocalizations. It might be movements, right? In the end, going back to the same underlying deficit. But if you all look at the surface of expressions of symptoms, indeed, it looks very mysterious. But so on those grounds, you really said, look, it's a network. It's a network deficit, right? So would you really describe it in those terms? You would see epilepsy really as a network pathology?
I would describe it as a network disorder. Technically speaking, so in this sense, it's not a disease. All of us can have the capacity to show an epileptic seizure. Some of my colleagues even claim that epileptic discharges or the capacity to show epileptic seizures is part of our dynamic repertoire, is part of the dynamic repertoire of the brain. Yeah.
Let's take the shortwave ripples in the hippocampus, right?
Yeah, but this more spatially localized. This is temporal features. The approach that we have taken is a network approach, and reducing it to statements such as it's the same deficit. It's simplifying it. The epilepsies are so different. They are linked to network activations that organize themselves. The underlying mechanisms may be completely different. However, the way how the network then expresses itself, this is then linked to the feature and the subsequent semiology for the patient. So this is then our entry point. My lab is a highly theoretical quantitative lab composed of mathematicians, physicists, engineers, in the institute working very closely together with signal processing engineers, clinicians, neurologists, neurosurgeons, all of us together housed in the same institute. We are not necessarily looking at the genesis of epilepsy and trying to identify the mechanisms underlying the genesis, at least the quantitative part of the group, but we are trying to understand, once a network is epileptogenic, the organization of the network that is linked to those features that we were referring to. And which means you could argue that each epileptic network is different. However, certain concepts and principles should be obeyed, at least as long as we are looking at it from the network perspective. I'm always coming back to the network, because if you look at an individual area with the type of approach we have taken, I cannot make a statement about that beyond some dynamic features, but I cannot make mechanistic statements about that. I can make mechanistic statements in terms of network language about the epileptic network. And coming back to your first question, this is where the power of our approach lies, where we can, despite the fact that we take a mathematician's approach to epilepsy, it expresses itself through network features. Yeah, this is where we can contribute. Yeah,
but now, for me, you're saying some really important things now, right? Because it's a multi-scale phenomenon, right? Because there's a local circuit that might generate some dynamics that has some knock-on effect on the surrounding network. So now I go from micro to macro. So there are two levels of organization we should worry about. But this microscopic, if you want, distortion and perturbation can come in many forms. That's what you're saying, right? But that's maybe not the most important part to understand or to control with respect to symptomatology, right? What you're saying is, what you really want to understand is then these knock-on effects across the network that will be invariant, independent of what this microscopic deficit exactly is. So this is the consequence. So you also see some sort of encapsulation of these two levels of operation. Because it also means that if as soon as a network kicks in and starts to switch itself into a pathological state or dynamic, it doesn't matter anymore what you will do to the local pathological circuit. The network now is pushed into this part of the state space where it will give rise to symptoms that you don't want to have.
This is more or less, actually, this is exactly what I was saying. So you introduce a language of micro-macro, so the microcircuitry. What I did not say, though, is that the microcircuitry or the microscopic understanding is not important. By no means. I'm saying it's not our entry point towards the understanding of epileptic networks. It's extremely important. And in fact, if you want to intervene with the epilepsy of humans or brain on the microscopic level, then pharmaceutics. Yeah, this is where the molecular entry points are. This is where you have signaling pathways that where you want to intervene, that you want to find the right molecule that has a right effect and reorganizes a microcircuitry and drives the area away from its capacity of discharging. Yeah, so this is important. But very often, this magic molecule that does this job, it's simply not to be found. And if you look at the development of drug history, so it goes back roughly 80 years, we have essentially 4 or 5 families of anti-epileptic drugs, with then multiple branching into subfamilies, etc., but not more. Yeah, and since 30% of all epileptic patients are drug resistant, there you have to find either new drugs or other ways of intervening, and this is where we are then coming in. And then it's not the microscopic level. Yeah.
Well, but there are two things here. On top of that, what are the side effects of these drugs that are being used? Are they harmless in that sense, or do people pay a price for using them?
I cannot tell you. This is not my expertise. Yeah, I do not dare to express myself on the side effects.
Good, but the other thing is that you're saying, I understand you have to say the microscopic generator or that kickstarts this whole process is important, because this is of course also reflecting how the field itself is organized. A lot of effort is being put into trying to understand the local genesis of the seizures. On the other hand, as you also said yourself, over the last 50 years, we've made actually no progress whatsoever in treating epilepsy. So
I did not say this. Over the last 50 years, I was talking about surgery, in treating pharmacoresistant epilepsy. And if you average across all epilepsies, then you have a fairly flat curve in the improvement in the surgery success rate, which averaged across all epilepsy types is around 50%. Temporal lobe epilepsy is better. That's 70%. Frontal lobe is lower, 25-30%. So let's say 50%, and it has not improved. But there was surgery success.
Okay, good.
Yeah.
I overanalyzed. However,
it's important. It's important. Yeah.
Sure.
Yeah.
No, that's fine. But still, the consequence is still that if you would have to choose today where you can have the most impact in trying to make progress in treatment of epilepsy, the network might be maybe a more opportune target than the local circuit. If you really want to make progress on intervention planning, treatment, symptom control, and so on, if I understand you correctly, you would have good reasons to go for the network as opposed to the microscopic generator of the seizure. Yeah.
I would be very comfortable with this state. I would be comfortable with this statement from the perspective of making the biggest progress. On the microscopic mechanistic level, it's important to continue. There's no question about this, but there are also many codependencies. Yeah. So this magic molecule, in the testing that is being performed, there are codependencies on other factors, etc. So it's kind of one of these blue sky projects that we talked about earlier, that we need a clear plan and agenda, organizing our thoughts in order to move forward more structured. On the network level, though, there we have at the moment, we may approach a tipping point. At the moment, we get more and more technology that becomes available to interact, to modulate the network. Stimulation is one, for instance. Different types of stimulation become available. Non-invasive surgery. Non-invasive surgery does not exist. Less invasive or minimally invasive surgery, such as thermocoagulation or laser surgery, where you enter into the brain through very little drill holes and are able to make ablations at little volumes in the brain that can help, again, network concept, to re-equilibrate the network. And there we have a battery of tools that allows us to give access. What we need is an understanding of how to use these tools in a well-informed manner. And there we are at the beginning, really at the beginning. We have realized that the epileptofocus is actually an epileptogenic network. It's an epileptogenic zone, spread, sometimes very focal, sometimes disparate with topologically non-connected elements. That the propagation network can be widespread, so it's clearly a network phenomenon. How can we make use of that without generating huge cognitive deficits? Because that is always, when you interfere with the network, you generate cognitive deficits. Can we ask questions or build decision-making software, guide the surgeon of making an informed intervention, minimally invasive, reducing maybe just the epileptic seizure propagating, and minimizing the cognitive deficit? So there are loads of possibilities, and this is where I hope that models can contribute a lot in the future. And then there will be other ways of interfering. It doesn't have to be surgically, but there may be some drugs that will be delivered locally, for instance, that can turn on off populations. So there will be other possibilities.
Proceuticals, right? It might all be non-invasive.
Yeah.
God knows.
Yeah.
But you're saying two things that really stand out, right? One, on the one hand, what you are announcing is sort of a revolution of moving away from this idea of the broken brain, like, oh, some molecule is missing, and if I just now reinsert that molecule, then everything will restore itself to normal. And from there, you move more to a network medicine perspective on brain pathology. And I think you are, I think, really are one of the big examples of that movement, I think, right now in neuroscience. And it's an important one. We have to really, I think, appreciate that, also see it as a very important development in how we think about neuropathology. Would you agree with that, or do you think I'm really exaggerating now?
I would agree with it that the network science is definitely entering into medicine, into computational medicine and the network thinking. Is it a revolution? It's changing the way how people think about brain disorders. Definitely in epilepsy, but also because of the successes about the progress we made in epilepsy, they start thinking about how can we think differently about other disorders or diseases also. So I agree with the fact that I wouldn't be hesitant to say it is a revolution, yeah, but it's definitely one of the hot topics at the moment. This computational medicine with a network idea, number one, and then link it to personalized medicine, of being able to render a network patient specific. Suddenly we talk about virtual brains, of my virtual brain, and it bears lots of promise.
Mm-hmm.
Yeah.
But there are two consequences now, right? So on the one hand, it implies that we move to a non-locality principle. In the past, with the broken brain view, you would also localize the problem somewhere at X, Y, Z. This is where we have to now fix the thing. While you are also showing, and also the results we might touch upon later, that these effects can be not co-localized with the position of your original, let's say, pathological circuit or lesion. It might actually, the real problem might be sitting somewhere else as a dynamic reorganization of a network, right? So we have to think about deficits much more in a non-local, global fashion. But the second thing that you say here, and that's what you show concretely with your virtual brain project, to make progress in network medicine or network neuroscience, we must rely on computational methods. We have to start to build models, and we cannot just follow simple lookup tables and heuristics to try to solve the problem. Right, so do you really see this as the key strategic step and the trajectory that we have to explore now of bringing computational models into the clinic to make progress?
I subscribe to that. Mm-hmm. Yeah. You brought up 2 points. The non-locality has been known actually for a while. This is not a new feature, yeah, or lesions or injuries in the brain at a particular location causes deficits in functions that are officially localized in completely other brain regions. So this is this has been well known. We can invert that and actually make use of this and propose, and this is far from standard, propose interventions at a different brain region that is actually not involved in the network disorder, but then has a positive effect upon the network organization and network function. Yeah, this is a logical consequence, isn't it? And this to find, and now I'm coming to your second point, how can we empirically find ways of doing this? For the negative parts, namely injuries in areas causing deficits in other subnetworks, we run into this through accidents empirically. But the positive, the interventional therapeutic aspect, we cannot run into by a coincidence. So we cannot simply operate blindly on human beings. We need a strategy. And how do we do this? In silico modeling. Yeah, we understand the network better, at least on the network level of a human being, the brain network, and we try to test out in silico new interventional strategies that cannot, for ethical reasons, performed in the human being. Yeah. And for practical reasons, not in the animal model, because you cannot stimulate all different areas. So all that remains at the moment are in silico approaches. But having understood these concepts, it brings up these in silico approaches as a vision for the future. We have the computational powers nowadays. Yeah. We have high performance computing structures. We have the data science that can support it. So I think it's a no-brainer, in quotation marks, that the trends are going into the direction of brain network in silico modeling.
Right. Yeah.
And the logic that I just proposed is completely independent of personal preferences. It's
but surprisingly, even though you call it a no-brainer, it's not widely adopted yet. So there are apparently some obstacles we have to overcome, right? So we're not there yet. So, and now, of course, the crux of the matter is, okay, what makes a good model? And in your case, what you made a very strong point for mean field models of the whole brain with emphasis on the neocortex, right? As a way to then start to get a handle on that, on the dynamics of the brain in health and disease. So why do you believe mean field models are the way to go?
On the level of organization that we look at in my laboratory, the activity of individual brain regions, as when it's being communicated to other brain regions, that expresses itself for the communication, is sufficiently described on the mean field level. We are validating this with high-dimensional microscopic simulations where we use single neuron models, not very detailed single neuron models, but spiking neuron models. And when we perform these very high-dimensional simulations and mimic these activations in the large brain network, it takes a long time to simulate. But we find so far the same consequences for the network and our understanding of the network's organization. For this reason, if you ask network questions, it is sufficient to perform the mean field modeling, at least in our hands, in our laboratory. If you want to pose these network questions and mimic them into, or not mimic them, direct them into other directions, probably linking to microscopic underpinnings, then you have to go beyond that. Yeah, we're not doing this at the moment. We seek the proximity to the patient and the clinic. Mm-hmm. Yeah, the microscopic underpinnings are in many cases performed in the experimental laboratory, not necessarily in the clinic, unless you extract human tissue, etc., etc.
Mm-hmm. So the mean field model allows you to collapse the microscopic dynamics across thousands, or not millions, of neurons into single state variables, right? Where you just say, look, this whole population here, I can basically capture one state variable that might evolve over time. So
multiple state variables. Yeah, not one, but multiple. Yeah, but not many. A few, a handful. Yeah.
But the question then becomes, what's your benchmark, right? So what are for you the dominant benchmarks to validate that very abstract, compressed view of brain dynamics? What is really the benchmark, the gold standard you feel today to validate such a mean field model?
What is being done in the literature and in the community is used paradigms such as stimulation, and stimulate a microcircuit composed of these millions of neurons, and then you get these firings of action potentials of spikes. There you have certain features, the raster plots with particular statistics. And
that's the way in which you visualize it or assess it. But would it be like the resting state network? Is that for you reference?
And this is where I'm going to. So this is what is being done in the community mean field. Mean field does not make any statement about networks yet. Okay, yeah. Mean field doesn't make any reference to networks yet. It's localized population. So most mean field modelers, mathematicians that work with that look at these features. What we do in our hands, the mean field has to represent the same propagation, for instance, through the network when you stimulate, and then the same sequence of brain regions is being activated. We have not looked at resting state activity, yeah. But what we have looked at is we take a very simplified network model with a reduced architecture and implement it with detailed microscopic neuronal features, and then with mean fields, and then we obtain under a parameter modulation, for instance, connectivity or time delays, we obtain the same behaviors, such as increase of synchronicity, the spatial reorganization at a particular value of the control parameter that we manipulate, etc. So we want to manipulate network features, and then we get the same behavior. This is what we have done. We have not validated this in full connectome-based brain network models where we have a full implementation of spiking neuronal networks with a connectome versus a mean field-based model. The mean field-based brain network model we have done, we have published with this for over 10 years, and it's well established nowadays. Many labs are working with these type of concepts. There are efforts within the Human Brain Project trying to generate the neuroinformatics frame in which we can do these high-dimensional microscopic networks, but it's not done yet. There are efforts from the Diesmann lab in Jülich. There are efforts from my group. There are mixed efforts in the sense that we build a network partly composed of mean fields and partly composed of these high-dimensional microscopic networks to demonstrate, this is called co-design, to demonstrate that we get the same dynamics. But all this is still unpublished. So these are efforts for validation, and it's crucial and critical, but efforts for validation for which the first results will come out in 1 year, 2 years, 3 years. Yeah, but it's all going in place. Yeah.
But this sounds like validation against more microscopic electrophysiology, right? Where you can capture that correctly. But given the huge amount of work already done in mean field models,
yeah,
I assume that within that community there must be a sense of having gold standards for the validity of these models. No, because there also have been plenty of publications of mean field models describing the whole neocortex doing something, right?
Yeah.
So today, if you today would have to list such a gold standard benchmark to calibrate a mean field model of the whole brain, what would it be?
It's here we are running into a situation where
you have to terminate the interview.
No, yeah, I'm leaving. Yeah. No, it's less the model that is the problem, but it's more the metrics that you use to describe the resting state activity and the data feature that you use to calibrate and validate the model. And one of the standards, and since you asked for gold standards, established today is in connectomics the notion of functional connectivity, which even there I said the notion of, because there are multiple metrics available for functional connectivity, and every single one of them is questionable to some degree, because these metrics collapse much of this information into very compressed object, and we know that mostly this very compressed object of functional connectivity requires stationarity. We know it's non-stationary. We cannot measure for longer than typically 20 minutes resting state activity in the human. So we run into issues of describing correctly or quantifying with a proper metric what we measure. And then you wanted to calibrate the gold standard in order to compare the mean field models. You could take some data fitting approaches. That's not good enough. In the naive sense of data fitting, you will always find a minimum, and or a maximum, depending on what you're looking for. And if you become more sophisticated, nonlinear with nonlinear Bayesian inference techniques that allow sampling on nonlinear manifolds, then we are not there yet that these methods can converge and provide us with good outcomes. The diagnostics is in place, but the methods may never converge in our lifetime. So at the moment, for this type of validation, it's not the mean field network model that poses a problem. It's in go-between, the metrics that shall be used for validation. How do you quantify a spatio-temporal trajectory evolving in a high-dimensional space that is undergoing a random process, with some deterministic features?
The situation is worse than initially expected, right?
Yeah.
Because even if you had the gold standard, you wouldn't even know how to sort of quantitatively match to it.
Exactly. Or I could even pervert it even more. I build a virtual brain. I tell you it's conscious. How would you test it? Yeah, you may not even be capable of recognizing. I don't want to go in direction consciousness. I just said conscious, but how would you? What type of metrics would you have to apply in order to go there? And I think this is something that we are suffering from in system neurosciences. We cannot simplify, in order to be close to the patient or to real-world applications, we cannot simplify everything to a state, and then we just describe the state or the statistics of the state. It's a dynamic process. So we need a process-based signal analysis.
Right. But I completely get that, and I agree with you. But so I'll confess that for me, the mean field approach has never been that convincing, even though it's always presented to me with a lot of confidence, right? Because in some sense, it has always been anchored to very slow signals. The majority of mean field models have been calibrated against fMRI data, right? Which is very coarse, a very a low-pass filtered representation, both spatially and temporally, of what goes on in the brain. So if we move to this low-dimensional state space, in some sense, many abstract models can do a good job, right? So in that sense, aren't we a little bit overconfident at this point in time about the power of these mean field models? I mean, you could argue that for the low-dimensional state space, they're sort of super powerful. They'll always work. They'll always capture these dynamics. For that, you have enough free parameters. Not a big deal, right? You can always do it. But for instance, look at, if you go to a more realistic state space, for instance, we work with stroke patients. We have shown recently that they have dysrhythmia, as in Parkinson's. So you get dynamic fluctuations in the cortex that appear transiently, and that are a result of what's playing out in the thalamus, and that itself is again a result of what goes on in the cortex, right? So you have rapid shifts in the dynamics that's playing out in a broad frequency range. So my mean field model would not trivially capture that just like that, right? I'm playing a different game now, right? So the concern I'm having, and so maybe you can resolve this for me. But yes, we've built all these tools and they're fantastic, and many people got tenure with these kinds of models. It's great, but it's all anchored to sort of low-dimensional dynamics. Where we really want to be are these, as you described, these high-dimensional transient dynamical states to which they might never really generalize. So would it not be wise at this point in time to say, well, we learned a lot using mean field models. We've identified a lot of the problem. We learned to appreciate the real problem we're facing, but maybe mean field models are now essentially not that helpful anymore as a tool. We should move on and think more about, let's say, multi-scale, dynamically configured networks that operate at micro and macro level simultaneously. Would you go in that direction, or would you still feel that there's a lot of leverage to be gotten from the mean field approach?
I feel there is still a lot of leverage to be gotten from the mean field for the following reasons. The way you argued is that the mean field modeling has found mostly application in the resting state literature of the fMRI. I would say no, mean field models have been used in the resting state network literature, and even very phenomenological models. As you correctly pointed out, a simple model is fully sufficient. We don't need 4 or 5 dimensional models. Just a simple phenomenological oscillator may already capture many of the features that are being observed via its network effects. And with that, I agree, actually. They are spatially filtered, they are temporally filtered, but and if you just look at temporal or spatial configurations, it's probably not very insightful what you do in the resting state network literature. You have to look at spatial-temporal features. And there it's becoming interesting. And there, having talked about the non-stationarities, you need nonlinear models that have certain characteristics that are then being informed by the connectome. But in fMRI, due to the nature of the signal, looking at non-stationaries and the fMRI signals, there we are already at the front line of the research. But having said this, mean field modeling has by far not just been applied to fMRI signals. This is fMRI modeling neurovascular coupling. Yes, uses mean fields, but you can have multi-level, multi-scale mean field models using the super, infra, and granular layers, and assigning a mean field or neural population, neural mass to each of these layers, interacting with multiple scales, interacting with different types of connections, slower and faster connections, in order to introduce a temporal multi-scale architecture in there, which has been very important. Example is, for instance, the work of Fabrice Wendling, who was following stimulation paradigms and capturing some of the response features. There we're talking about neuroelectric signals on timescales that are relevant for the processing timescales we encounter in the brain, for the spectral features that we are familiar with, for the different bands, rhythmic bands that we are familiar with. And there, these mean field models are not just simple scalar elements that are just shifted around on a linear equilibrium point and reorganizing the networks as in the resting state literature. No, here we have to work with detailed organizations that can be stimulated, that propagate through the network, that have continuous propagation through the gray matter, that send signals through the white matter. This is being done. I agree. It is the beginning. I fully agree with that. But your question was, can we still gain some leverage out of this? And yes, yeah.
Yeah, but no, what I see there's a sort of a conceptual problem here, that the definition of mean field model is a bit shifting, right? So you have this famous quote from Norbert Wiener, but the best model of a cat is a cat, and preferably the same cat.
The same cat. Yeah.
Right? But what he means with that is, to model means to abstract, right? And in some sense, what I hear you say is, well, as long as we abstract, I can call it mean field, right?
Why do you hear this?
Well, because you're saying I have mean field models that would take into account organization at different layers in the cortex, specific cells, and so on. It just means you change the granularity of the averaging that you perform.
Is what we are performing, yes.
So
that they have certain properties, such as
Sure.
adaptation, And then in the different layers, you have different populations, and this is being reflected.
But that means if you go to the mean field models of some time ago, that was more a closer link to, let's say, statistical physics.
Yes.
They really made those, I think, a stronger claim of the boundary, because those mean field models also had the objective, or at least the ambition, to collapse them into some sort of master equation with which you can really describe the macroscopic dynamics of that system. So it was really the search for this abstraction to also in the end have an analytical handle on that system. Well, what you're saying now, the way I take it, which is not necessarily criticism, it's just it just means we have to think a little bit what we mean exactly with the mean field model. Is, as long as I'm averaging, in some sense, as long as I'm collapsing detail into state variables, I'm using a mean field model, and therefore the mean field model can scale and be diversified in all possible directions. But if something starts to represent everything, it represents nothing, right? So what then do we really mean with mean field? And maybe we should then also, would it be useful to start to then also give more specific labels to this granularity of modeling, right? Like the number of free parameters we are going to allow, the commitment to analytic solutions or not, right? So don't you feel that you're sacrificing a little bit the specificity of the meaning of a mean field approach?
Only to... No, we are still in my comfort range. I would not be willing. My comfort range is probably limited up to this point where we go across the individual layers. I would not go any further in terms of granularity, because at some point it doesn't make any sense. But in terms of abstraction, it again reduces to what I want to explain, what type of signals I want to explain, what type of phenomena I want to explain. And the explanatory power of a mean field benefits from the layered organization and propagation through the gray matter, but also then through the white matter fibers. But I would not be comfortable of deconstructing it any further for two reasons. It may not any further deconstruction or specification may not help in the explanatory power of this the signal that we want to explain, number one. And number two, at some point this mechanism of averaging, because of all the detailed architecture, physiological architecture that is present, we have glia cells, astrocytes, etc. It doesn't make sense anymore. Other effects would have to be integrated also. It has its limits. Yeah, you have to have an sufficiently coarse object in order to average across its inner organization. Otherwise, it doesn't make sense. Yeah,
but this is interesting, right? Because it also means it doesn't make sense until it does, right? So, for instance, if for an epilepsy case, I would find out that some sort of infra-supergranular layer distinction would be really critical, then you would be happily embracing it. Then you would be happy to exceed that boundary that you now draw.
Pragmatically thinking, I would probably, consider it. I would have to be convinced that it does matter, etc. Yeah, of course. Yeah, exactly. Yeah, exactly. And I'm not saying that this distinction does not matter. I have certain objectives with the research I want to do. I want to reach real world questions in the clinic. So I'm building the tools that help me to address this type of questions.
Right.
Yeah.
So I get it. But this is important. That's also for the field of mean field approaches. I think it would be useful to have that discussion to also see, okay, maybe we should look at different types of mean field models and also try to understand their interrelationship again.
Mm-hmm. It is being actually done, Paul. And there is a community working on this. Imagine heterogeneity. Neurons in a population are not identical. Yeah. If you just take the most simple feature of them, the threshold distribution. Yeah. How do you take it into account? It actually generates, if you have this diversity or no dispersion within the population, which in physical space is zero dimensional, but if a dispersion of thresholds, it already generates a huge complexity in the dynamics. I'm talking about the model now. Just in the model, we know that you can have chimera states. The same population, actually, it's in this case, it's not chimera states, but you can have clustering. Yeah, in the behavior and within the population, you get clusters of similarly behaving neurons due to their similarity in their physiological constants, but you cannot cannot average over it because some are spiking regularly and others have the irregular spiking frequency that we know, like a Poissonian train. So this, what would I do there? And again, if I am aware of these things, I split it in multiple mean fields. Yeah, and then which means I complexify. And this has been done. This is one mean field model that exists, and it makes sense up to a certain degree. But once it becomes non-handleable anymore, then its pragmatic use, its pragmatic added value is not there anymore. And I would not support this approach to go any further. Mm-hmm. Yeah.
But now, one thing you did to give more structure to your mean field model interpretation was to move towards very distinct models of different kind of oscillators, correct? And then to use these to sort of, if you want, constrain the function interpretation and then use that again to go back to your epilepsy physiology to say, I don't need to model this as some mean field network. I can actually re-describe the mean field model as an underlying oscillator, right, with different characteristics, different state variables. And the question is now becomes, well, this whole family of oscillators, which one best describes the specific bit of epileptic state that I'm trying to describe, right? So why did you move in that direction? Why did that become then the next step? Because in some sense, you then gave up the literal whole brain mean field model. We said, no, I'd use that to calibrate my oscillator model. And the oscillator model becomes now my reference to interpreted data, right? So actually you have collapsed again the mean field model of cortex into these oscillatory models, right? So has that given you leverage? Mm-hmm. Or is it sort of more like an experiment that's underway right now and it might not really work out?
Mm-hmm. It's interesting that you ask this question. It's actually the way how science sometimes goes. It can be very exciting when you look backwards. We started off with mean field models, again driven by a particular question in the context of epilepsy, that is a propagation through the network. I recognized that a important fundamental characteristic is missing in these mean field models. It's simply not in there. Through the averaging process, through the methodology that is being applied, you essentially lose it. And it is an additional dimension, an additional degree of freedom that we refer to as the slow variable that acts upon another timescale that is not part of the classic mean field averaging, but that has certain characteristics that guides on a slow timescale the mean field dynamics, if you wish, through a sequence of behaviors. And then also the system from seizure onset through the evolution during the ictal state all the way to seizure offset. And that was not something we could overcome. We could look into physiology. We knew there are slow processes. Classics are extracellular potassium, the work of Uwe Heinemann, etc. There is knowledge in there, but that would require an additional mechanistic bottom-up approach developing this, and it's multifactorial, as we know. We ask the question, can we, since we are interested in the network question, can we find another approach, another perspective, still capturing this additional feature in there, justified by a scientific perspective, but maybe different perspective? And there we turned to mathematics. And since we were looking for a slow variable, we tapped into the theorems of nonlinear dynamic systems, fast, slow systems, and we made use of that to abstract entirely away from the physiological interpretation of these variables and looked at the dynamic structure of the representative of this mean field that we needed. Yeah, and we did this very, very systematically, and we learned a lot out of this. But it gave us also a new perspective about how to look at seizures, of what features to look at seizures, not physiologically motivated, not mechanistically motivated anymore, but purely dynamic features. And that started a trend in the community in terms of slow variable, onset bifurcation, offset bifurcation, etc. So that is becoming a language now. This is exciting. But then looking back, I still remember how I went to my collaborator, Christophe Bernard, who did the physiological testing in the hippocampus. And we were discussing these dynamic features, that the meta mean field, or this expanded mean field representation expressed in terms of phenomenological variables should have. And I said, Christophe, I have a problem with that. There should be a baseline jump that you see in your data in the time series, because the bifurcations, the dynamics that we find, there is a baseline jump. And it's not in the data. Can I somehow sweep it under the carpet, maybe hide it in the signal to noise ratio? Or what can we do about this? And he said, Viktor, but look, these are AC data that everyone is recording in AC, but I can make the same recordings in DC. Yeah. So he went back to the lab. Yeah. Did the same recording in terms of DC. And because I told him about the slow variable, at the same time, he measured also oxygenation and ATP consumption and came back to me and showed me the same recording AC. Yeah, there you didn't have a baseline jump. In DC, you had exactly the baseline jump at seizure onset and offset. Hippocampus in tutu in the rat, exactly as I expected. Very beautiful. And the oxygenation and the ATP consumption traced out very beautifully the time course of the slow variable that we expected. There you could say this is not too surprising because it's, of course, linked to energy consumption, and it has to happen when the tissue fires very fast. Well, but I'm sure it's not the slow variable, but these are representations or expressions thereof. But it became consistent and things came together. And then we went into human tissue. We contacted other institutions, Ikeda in Japan, Milan Brashdil in Brno. They had also DC recordings from the human tissue. And then for the seizure types that we were looking at, we found the baseline jumps. And this was coming from the dynamic structure of the system. And this was really unexpected, very beautiful, and gave us confidence. Different elements started coming together. And now people, my colleagues, are looking into possible realizations of what we call the slow variable. Yeah, I mentioned extracellular potassium. Definitely glial activity are good candidates that may that are linked to the neuroelectric discharges, etc.
Right.
Yeah.
But do you believe that it's the slow variable that is also of most relevance in with respect to the propagation through the network?
I have to hypothesize.
No, sure.
You ask believe. Yes, I do believe that the slow variable plays a particular role in this. We know that the glial network is tightly connected to the neural network. It's evolving on a slow time scale, much slower than the neuroelectric discharges. We do not know enough about that. However, I'd like to point out that when seizures propagate and spread, sometimes everything discharges, the entire network discharges at the same time. Sometimes it starts discharging at a particular location. 1-2 seconds later, it recruits another area. Then it disengages and it recruits another area. So you have a spatial-temporal organization on the timescale of seconds. Yeah. What are the mechanisms that are linked directly to this? You need to have some timescale hierarchies there, not necessarily separate and expressible in physically separable quantities such as region 1 and region 2, but more informational. But there must be a timescale hierarchy in order to describe this multi-scale behavior. Yeah.
But the consequence of that would then be that you also look at a new generation of network or whole brain or whole cortex models where each node in the network becomes a distinct oscillator, right? Coupled through whatever the connectomics has told you. No?
Yeah. Plus a slow variable that is locally connected to this oscillator through the connectomics, and then this oscillator is coupled through the connectomics, as you point out. So we look at a co-evolving, a new form of mean field models, co-evolving on 2 timescales, fast and slow, localized in tissue, in space, communicating at least through the connectome, maybe in addition to this, also at least locally through a glial network. Yeah.
But
that would be a new generation of mean field models.
Exactly, yeah, absolutely.
Yeah.
But would every node now cycle in a state-dependent fashion through different models, through different oscillatory models? Or would it be just one oscillatory model that is just pushed around in its state space because of the external perturbations?
I do not know. I cannot tell you.
Okay, because the oscillator you take for the node where you have the seizure origin is in some sense a pathological node, right? Where you see the DC shift and the slow variable and so on. This might not necessarily be the right oscillatory model for all the other nodes in the network.
Yes.
Okay.
Yeah.
So there's now, that might be interesting. So that might look like every node is, the dynamics is potentially represented by a certain set of oscillators, but now dependent on the state of that specific node, I'm either in one or the other.
Yeah. The way we have looked at that so far is we looked at topological equivalence of the parameter spaces. I don't want to make it too abstract, but it's like you can identify certain features in the properties of the oscillators, and then you know that in the neighborhood of this feature, in this case, it's a type of bifurcation, a codimension 3 bifurcation, Tarkans-Bogdanov. You know, in this neighborhood, all the behavior and all the classes are more or less the same. Yeah. So it's not multiple oscillators, but the qualitative behavior of the same oscillator changes as you move around in this type of neighborhood. So it's a local statement, and if you wish to call it a pathological oscillator, I'm comfortable with that. However, I'm not comfortable with making statements that are not somehow in the local neighborhood, but that jump into completely different behavioral repertoire somewhere else. I simply cannot make any statement about that. Yeah?
No, sure.
I do not know. Yeah.
But we're free to speculate.
I'm free to, you want me to speculate?
Of course.
There is the way we looked at it is we talk about oscillators, and we built a generic canonical model around a very characteristic bifurcation point, which is a kind of an anchoring point in a parameter space. This oscillator has no idea that it's supposed to be pathological or epileptic. At the end of the day, it's a mathematical object that has certain properties that we are manipulating, and that are based on certain proximity principles. There are consequences for its behavior. And actually, there is just a finite number of ways how bifurcation lines can collide. And hence, there are not so many types of different behaviors that can occur. It's almost evident that there is a limited repertoire of behaviors in there. So, having said this, and they are interdependent. Yeah. So, having said this, why I'm speculating, this line of reasoning does not apply only to epilepsy. What's about physiological oscillations? What's about up and down states? What's about spindles that occur? Can we apply this to physiological objects or physiological oscillations, then characterize them in a similar way? Maybe, but it's a little less controlled. They appear sometimes, they do not. We know they are linked to sleep and wake changes. In the different sleep stages, there are different behaviors. A similar way of thinking should apply to that also, and may even, and I'm speculating even further, require the need of a slow variable. So I would even be comfortable to speculate that we need to generalize this way of thinking of a co-evolving, at least two-tiered temporal scale mean field model to physiological applications, and say it should apply actually also to that. Yeah,
that's very beautiful. Huh? But now look, so we made quite a tour here, trying to understand epilepsy. The critical step was to move to a network perspective, right? To a network science perspective, for medicine perspective of epilepsy. And now, of course, then we have to think about what at the heart of that stands computational model-grounded approach. So, okay, what are these models? But now it was up to you, and we really think about the full-fledged deployment of this way of thinking to the clinic. So we have infinite time and infinite resource. Now it's there in the hospital. What do we see? How will this translate to a technology really at use in the clinic or at home? How do you see this realized in the real world down the line?
Beyond epilepsy, or?
Well, let's start with epilepsy.
The way I would like to see it is as a decision-making system that in the real world, we're talking about a real-world application now, that aids the clinician, enters in the decision-making process during the patient management conferences. They develop confidence upon this software. It will probably express itself as a software, and feedback their competences in order to make it better. But at the moment, it's extremely primitive. Where I would like to see it would be as an in silico platform where we can perform testing and maybe optimization of procedures, but that requires validation, that requires confidence that the predictive value is sufficiently strong enough. There, we cannot bypass the animal. However, we can see it as a means at some point, once we have generated the confidence, to bypass animal experiments, because they will be substituted by in silico experiments. And then we will have in silico brains of individual human beings where we can optimize procedures, maybe rewire, maybe discover new therapeutic interventions, but we have to lean out beyond what we are out of the window, beyond what we are doing right now. Like with a lesion, as we talked about earlier, lesioning in an area that is not impacted by the impairment. So we need to go beyond that. Yeah. And that we need to find good strategies how to do this. Otherwise, we will never have trust and faith in an in silico platform for a particular patient. Okay. Yeah. So this requires a strategy, confidence, trust building.
Mm-hmm. But especially with the clinicians, right? So you're not going in a direction of having devices that will work directly with the patient to help them to control their epilepsy. You see it really more going into the clinic to decision support for the clinicians to decide on interventions, right? That might mean non-local interventions in a network affected by epilepsy.
Just as an example, the non-local part, but there may be other ways of dealing with it.
That would be, if I generalize from that, which I have no difficulties in doing, maybe that also means that at some point we do need to carry a model of our brain as part of a medical record because we might have a lesion somewhere. And then to figure out what could go wrong, I need a reference. And the reference is the model of a cat is a cat, and preferably the same cat would certainly hold for us. Right? So this might be then also an automatic consequence of the approach that you're following now. Otherwise, I have no reference. Which
would be wonderful, wouldn't it be? Then we have a reference brain for you that may have been fingerprinted, data fit, where the parameters through a battery of cognitive tasks, or maybe stimulation paradigms, your brain has been, your virtual brain of you yourself has been calibrated and the range of parameters has been identified. Then the model parameters themselves become a biomarker for your health, because maybe we could imagine a ongoing online calibration of the parameters of your brain model on your favorite app. And then as you get tired, depressed, I don't know what, the parameters get out of a range, etc., etc. You could imagine, now we are dreaming, now we are speculating. But yes, a virtual brain model entering in your medical records, I think this is not necessarily a bad idea.
Right. But the cool thing is that automatically and for free, you achieve the post-humanist dream of downloading your mind into a computer.
Who has talked about the mind?
Well, we think it's isomorphic. Yeah. But then that mean field model you have in my medical record better be correct. Otherwise,
the mean field model is a model of a regional activity expression, and you know that very well.
I'm just provoking you.
Yeah.
But look, so Viktor, this is really very exciting territory, and you made huge strides in really redefining the challenges and making real concrete progress on answering those challenges and understanding the brain and also having clinical impact. So if we would like to follow in that direction, what would be Viktor's law that we have to adhere to?
Can you be more specific? If we will follow into this direction, which direction? Virtual brain, the science,
yeah. Virtual brain, yes. Yeah. So we want to go to what's Viktor's law that I should follow
in order to
make progress, to achieve the dream you just declared, a virtual brain in every medical record.
Mm-hmm. I don't know about Viktor's law, but go beyond states, think processes. Yeah. I'm trying to formulate it as a law. Yeah. But go beyond states, think processes, let them be spatiotemporal or not. But we need a dynamic way of thinking, or thinking of the dynamic brain. And I looking back at the history of science, this states approach has hampered much of the translational capacity that neuroscience could have had. So let's think in terms of dynamics and not just jargon, but put it to use and explore the powers that we have in terms of dynamics to ask different types of questions. Yeah.
Right. So the last question for me is, so you run a big center there in Marseille. You have a lot of machinery, you have a lot of support. So you can really advance this science at quite a pace. So 4 years from now, I'm going to go visit you in Marseille to see whether you falsified or verified a key prediction that you're going to share with me now. So in your program, what's the most central hypothesis you want to see tested in that 4-year time frame?
I would be, the most central hypothesis in a 4-year time frame, in the way how we think in Marseille about epilepsy, and here I'm focusing it on epilepsy, is that we can use the network description to patient-specific connectomes within the networks, that it has a real explanatory power, and we can make use of this explanatory power to help the patient and improve the outcome of the therapy, which means if we use patient-specific and not generic connectomes to build virtual brains, we can make better predictions about what should be done in order to help the patient. When you come in 4 years into my lab in Marseille, I would like to present you with 300 to 400 patient cases where I have convincing metrics, convincing statistical significance that demonstrates unambiguously that using this patient-specific connectome linked to dynamics, dynamic mean fields, has actually improved surgery success or interventional success. Yeah.
But wait, let's be specific now. Today's success is 50%, you're saying, right? Of surgery.
Average across epilepsies, etc.
So where's the number going to go? The success rate?
Do you want to pin me down on a number? 60%. Improvement by 10%. I'm really shaking this one out of my sleeve. You know that very well.
Of course, but
But I would like to
bet. Yeah, we need a bet.
Okay, 10% improvement, 400 patients in 4 years.
Fantastic. Viktor Jirsa, thank you very much for this conversation.
Thank you, Paul. Yeah.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.